Okay, so this is our eighth session of tips and tricks, which is super. And I know many students have benefited from either joining the sessions or listening to the videos, so that's great. But it's pretty open-ended, not super formal. And that's, the idea in general is we want to kind of look at a few things, uh, particularly tonight with regard to Lab 7. So we're fortunate to have with us our Distinguished STEM Leadership Fellow, Jenny, who also sits in our Tuesday, Thursday evening section. So without further ado, I'll turn the platform over to Jenny.
Okay, so I'm just going to go over major questions that you will be doing for Lab 7 and what are the some of the errors that usually everyone faces. So basically when you open, you just will just run everything. The first two blocks are just for you to run it. You don't have to do anything except writing your name. And you can go over these details to know more about what this lab is about and why we are doing it and how the data is used to generate trends in the upcoming future. So this is the table that we will be working with. It has years from 1753 to, I believe, 2000 something. I'm not sure, but yeah, basically starting from 1753, and it has a lot of countries and average of temperature for each month as well. So you can basically just look at through this, and here we are kind of uh making the countries out, expanding everyone. And then there are if you look through carefully, there will be some countries which are repeating. Like France is repeating twice, so we want to make sure that that is eliminated. So this is just a code that will eliminate all the repeating countries and sort it by continents. And this is basically finding the average temperature from the year 1850 to 2000. And for the first temperature, what you need to do is calculate the average temperature, which is not that big of a deal since you have duals you might have done in the previous lab. So you just basically use a simple NP mean functions to find it. For question 2, you will be plotting a histogram, which is pretty simple as well. You will just use plot function, or you can just use dot histogram depending on whatever you're comfortable with. It should look something like this, and it might be different on based on if you're changing some of the values in the question 1. So you you can look at here as a reference, but it's not necessary that your outcome should be the same. And it also asks you for a reflection. So make sure that you are doing this part, or else if you skip this one, it will give you test failed. I have just written be sure to write a paragraph about it. I've just written a few sentences. That's why I'm getting an error about it. But once you make sure that your reflection is up to date and complete and satisfies the requirement, you won't get this error. Okay, moving on. So question 3 basically asks you about describing hypothesis based on your outcomes in question 2. So you have to describe hypothesis and null hypothesis. I've summarized what both of them are. So hypothesis is just in mathematical terms, the temperature difference should be greater than 0. And null hypothesis is just, it should be equal to 0, which is not possible. It is just a ideal situation. But this is basically, you just need to summarize it in your own words and make sure to just remember the word requirement, and it shouldn't give you the error. And it also if you, I believe there should, if you don't know more, if you want to know more about what hypothesis is, you can Google it. There are lots of videos about it. So, and moving on, we are just uh, testing our hypothesis if it is accepted, rejected, if whatever hypothesis that we are working with, how it is accepted or rejected. And if you read through this, it's giving you general formulas for standard deviation, standard error, difference between two sample masses, all of the stuff. So, and everything is defined, so you don't need to define anything. You can like look through the formulas to answer next questions. It is pretty simple if you want to find, let's say, standard error. So you will first figure out what this S stands for and what this N stands for, and you can just simply divide it and you will sort of answer the question. It's not that much of things to do here. As you can see, everything here is defined. This is already in your program as well, so you don't need to worry about that. So here it says calculate the t value. So you will just read through this. So t value, what is t value? It is basically the mean difference divided by standard error. So that's what I did. And like I got the value. Again, it might differ for you if you changed or altered some of the data in here. You don't have to make sure that like it is exactly the same. So just keep that in mind. And as you go down, there are like different uh, p-values that you have to find and make sure that you're running each and everything. I've already run it, so I don't need to run it again. But if you do run it, if you miss one or two, it's gonna give you an error. Okay. So the question 5 basically asks you like the p-value is the probability that observed the temperature increase are random. Obtain the estimate of this value from the table. So if you read here, like it says degree of freedom, then there are like two types of p-values, and you have to find the if whatever your p-value or t-value is. So if it's like greater than 2.58, then your p-value will be 0.5 based on this table. So basically, you need to create an if-else program to find your p-value based on the t-value. So you will look at here and compare the value and just go from there. And basically here again, you have to like write the whatever you get your value as and just explain it. And it says, can we reject the null hypothesis? Again, null hypothesis is nothing. It's just the total difference should be 0, which is not possible. But if it is for you, you can definitely work that out or maybe look back again if you made some kind of error. And it should, once you like complete this paragraph, it should say all the tests are passed. Simulation approach. Now you will use the second approach of finding p-values. There are like two different approaches of finding the p-value. First one was like estimating the t-value, and based on this, we are finding the p-value. Now we will use different functions. So basically, you are just going to run this again. It will just base. So here we are like not running anything, or like you don't have to create a program or something like that. Based on whatever values you get here, you have to kind of explain it. Why did you get such values? So that is just what you have to do. Write a paragraph and make sure that you are within the word limits. And again, you will run this. And again, it asks you to make a histogram. You are you should be pretty comfortable with making histogram. It's whatever method you are comfortable with. And it should look something like this, or it might differ depending on your values again. So basically, all the next question are based on what you do above. So like just go in a series, and if you are missing something in between, just go back, look again, and you should be able to solve everything. There are a lot of questions where you need to write a reflection. So make sure that you are just completing the paragraphs. Other than that, all the rest of the questions are pretty simple. You don't need to like generate new variables or anything. Everything is defined. So you just need to like read through the description that is given to you and kind of work through it. That's basically it for lab 7.
It's extremely helpful going through. And as Jenny said, it's so important to the reflections are particularly important here because there are a few coding steps, but not a huge number. It's more looking at the outputs that you get and how you internalize them and come up with those open-ended responses. So that's great. Here we will look at a function, and this function is specifically designed to simulate the roll of a six-sided die. So we have input arguments, which include MOD, short for modifier, and num. Num is short for the number of rolls or observations that we would like to obtain as output from the simulation. I want to think about a function as having a name, which is in this case sim underscore roll, and then it will have input arguments. These arguments will control the output of the function. The heart of the function contains the assignment to the variable rolls, and this is done by using numpy.random.choice. And here we use the possible rolls defined external to the function. It's possible and perhaps preferable to define this within the function, but for simplicity, we've done it in this manner. And in the numpy.randomChoice, we have a second optional argument, which is the number of elements of the resulting array, numpy array that we want to produce. And that is controlled by the input argument num. Notice the num is the same argument as shown as an input argument to the simroll. And then we have the mod, where we add that to each element of the randomly selected array containing the possible rolls. And those will be randomly selected from the subset of possible rolls 1, 2, 3, 4, 5, and 6. Then the last line of the function will be the return. And what does it return? It returns what we want the function to output, which is rolls. Now we can see further how this process works. So when we call the function, how do we call the function? We simply type the name sim underscore roll, and we use input arguments in replacement of the MOD and NUM or num from above. When we call specific arguments within the simroll, we get back the output array, which internal to the function is called rolls. When we're working with the function in the future, as in this below example, we see those rolls listed. And in fact, I have received 10 rolls, and here the modifier that I have given is 0. So these numbers are selected randomly between 1 and 6. So that's what I wanted to show you in terms of working with the function in a little bit more detail. Last example, so I'll just close a few things up here so we can see this a little bit more cleanly. The couple things I'll call attention to really quickly here. In this case, I'm carrying through what's done in Lab 6, but doing it for 6 die. So first off, a good way of creating that 6-sided die, again, is using np-arrange. And then here's an example of a function which can simulate the roll of a 6-sided die with a modifier given and a given number of rolls. So this function is pretty self-contained. Here we can take advantage of the fact that the numpy.randomChoice, we can use those possible rolls, and then we can give a second argument, second argument, which is the number of rolls that we would like. Where does it come from? It comes from up here. Remember, when you create a function, that every one of the arguments should be used somewhere, okay? Within the function, because there's a reason you have given those arguments. One is because those are the things that you would like as inputs to the function, so you can get the output from the function, the output being the rolls. And secondly, we don't want to constrain the function to only work on one circumstance. So someone might be tempted, for instance, in the early questions in Lab 6 to say, I want 7 roles. So then you would put just 7 here, but then the problem is it always will operate for 7, okay? So that's why we want to put the number here and then run that. And then we can see each time I run this, here I have a modifier of 0 and I'm requesting 10 roles. I can, because the function is so flexible, I can really quickly change these parameters and get very different types of outcomes. So here I have a modifier of 5. Now this is a 6-sided die, so you can see the results that we would get here. If I have a modifier of 5, the lowest die roll I can get is indeed a 6, because the die will roll anywhere from 1 to 6. So then if we add 5 to it, we're going to get 6. So if we have a minimum die roll, then that minimum of the data set will be 1 greater than the modifier. Here we can plot a histogram, much like Jenny showed in the case of the Lab 7. We can carry this command, or alternatively, in this case, we don't have a table created, so we would rely on the plot plt.histogram, which uses the matplotlib module. So here we can see, now in this particular case, I've given a modifier of 0 in this case. It's a little hard to see on this histogram, but indeed, if we look more carefully, this is 0. 1 is halfway between 0 and 1. So this block here corresponds to each time a 1 was rolled, 2, 3, 4, 5, and 6. So it's a little hard to interpret. We could do a little bit better job with the histogram, but that would require some additional commands in the plotting command here. So actually, I can already see we might be able to improve it slightly in this way. Yeah, that looks a little bit better here. Not perfect, but a little bit better. So here, if I have a modifier of 2, we can see the offset here. It starts here at 3 because 2 is the modifier, and then if we add 1 from the lowest die roll, we get 3. If we take the mean of 1,000 die rolls, we get 3.48. We can compare that with the mean of this, which is the mean for taking 1, 2, 3, 4, 5, and 6. We take the mean of that. That is the average of a die if we were to roll it an infinite number of times, because each outcome is equally likely. When we simulate this way, even if we add several more zeros, we get closer and closer to 3.5, but we're never going to quite get there because we can't simulate an infinite number of times. And as we go to fewer and fewer times, let's say 10, our number diverges further and further from the theoretical value that we would be interested in. Now here, with regard to Lab 6, we can see that the mean that we might get here is 10.5. Now, if we did the simulation, again, if we keep doing more and more rolls, we're going to get closer and closer to 10.5. But it turns out that the check in the question in Lab 6 is looking for exactly 10.5. So future updates of the lab, we might make it more reflect the words above it, which says you should simulate a large number of rolls, more like we did up here for the 6-sided die. But the reality is the check is looking for this. I believe in that case, the label is mean 20 in the lab. So that's a little tip on that last part. The rest involves the work with dictionaries. You can look to example class 15, class O15B, which is what this particular notebook is. See up here. And within there, you can see most of the things I've put here. I've modified them ever so slightly in front of you. But the idea is to play around with these things. It's in terms of a 6-sided, but you can move it to a 21-sided if you care to, and model your code based on that, should you be having problems there. In terms of the dictionary, there's a couple examples down here really quickly. We have the Darwin words, and here this is not a function, but this is a iteration through each of these Darwin words. Each word in this book, and this book, Darwin words, oops. Yeah, the way I opened it, it caused that. But since we're short of time, I'm going to just ignore that error. This is the number of words, 155,622. So here in this loop, we can look at each word in Darwin words, we can make them lowercase, and we can create a new entry in the dictionary. Through this command, we add 1 to the entry. If it does not exist, it becomes 1. If the entry already exists, we will add 1 to it. So how does this work in reality? We run through that. Now we see there's an entry in the Darwin dictionary for birds, and the value for that entry is 83, meaning that birds is in Darwin words 83 times. If we remove that, we find that bird is in there 17 times. And then the last thing I'll show you is these are each of the entries. Now they're not sorted. If you notice, this is actually the order in which the text occurs in the Origin of Species. But these counts are reflective of the subsequent times that the word on was located in the text. And it's 1,519 times. The, no big surprise, is found a lot more times. So that piece we can remove words such as the, of, by, or, in, for. Several others, these are called stop words. We can remove them, and then we can get a clearer picture of the frequency of the different words in the text.